Hello everybody, welcome back to my Gregorius Maths video. Happy New Year, I guess. Well, today, I'm restarting. I'm restarting an old series. Well, not that old actually. In the grand scheme of things, not that old. But I'm restarting, revitalizing the theorem of the week, and hopefully, I think in principle it's a great way to sort of keep a regular upload schedule if okay, I just have to make a video about one theorem a week. Because 2024 was a bit of an abysmal year for Gregorius Maths, I'll be real. But anyway, we're back in business, and I thought the best way to kick things off in the new year would be with the Salamander lemma. And the reason why if I may give a shout out to two members of the Discord server, both Dennis and Eso, some pronunciation, for suggesting this, because it's quite unknown, so I'm providing something new to the YouTube landscape, and B, well, it just covers it's sort of like the big sort of general version of the sort of diagram chasing theorems that you can prove, like the snake lemma, 4x4 lemma, I think, the even the long exact sequence in homology. You can show them using the Salamander lemma, and I think that'll be a different video for me to do, to use the Salamander lemma to prove statements in homological algebra. But yeah, it was quite hard to find resources on this because, well, I did a little quick search on YouTube, and the first thing that came up was that clip of that guy of some movie where they talk about the snake lemma, which is actually kind of crazy. I didn't know that a movie would involve the snake lemma and actually be accurate, but that was pretty cool. And then I looked it up on Google, and I saw like an NLab article and one sort of paper, like a blog post and a couple of Math Stack Exchange posts, but it didn't seem to be covered in any of the like sort of homological algebra texts and stuff. But I think it's quite a neat result, and yeah, I think it would be quite fun to go through to reignite Gregorius Maths in the year 2025. So let's do it. We begin by considering a double complex, and so what this is you've got you've got chain complexes going up, chain complexes going across. So we'll be of the form, so we've got a n m, across we'll go a n minus 1 m, so on, so on. We'll also have vertical maps, so we'll go from a n minus m minus 1, so on, a n minus 1 m minus 1, so on. We'll have vertical maps, so we'll call the vertical maps dv, the horizontal maps dh, and yeah, we've got vertical maps going in, out, and as per usual, these chain complex maps, so the dv's and the dh's, they all square to 0. So if we do dh compose dh, we'll get 0. Same thing with the dv compose dv. And I'd also like to impose that these squares, so we'll get infinitely many of these squares, all of them commute. So if I do dh and then dv, that's the same thing as doing dv and then dh. And I think some authors use the convention that this anti-commutes, so sort of like dv dh is the same thing as doing minus dh dv, but I'm just going to let it commute because it's easier for the sake of this video. Now, what we're going to start off by doing, because the Salamander lemma requires a few definitions, we're going to start off by zooming in on one element of this double complex. We'll call it A. Now, if we look at A, we have a few maps that we can consider. We've got the horizontal ones going in and out. So we've got dh in, dh out. we've got the vertical ones going in and the vertical one going out. And then we also have two more. We've got the diagonal one coming in, which I'm going to call DD in. And that's just the composition of a horizontal and a vertical, or a vertical and a horizontal, because the squares commute, same thing. And we've got a diagonal map going out, like so. And from these maps, we can form four definitions that we want to consider for the Salamander lemma. Now, what are these four definitions? Well, they're the following. So we have the two typical definitions of homology. So we've got the horizontal homology, which is just, as you'll expect, the kernel of the guys going out horizontally mod the image of the guys going in horizontally. So kernel mod image. Similarly, the vertical homology is the kernel of the guys going out vertically mod the guys going in vertically. And then we have two new definitions. The first one is called the receptor of A. Now, the receptor of A, what it does is it considers both, so it's the guys that are killed by both the vertical map and the horizontal map. And then you mod it out by, okay, this red pen is dying. And then you mod it out by the image of the guys that are coming in diagonally. So you take the guys in here that are killed by both the guys going out, so both the horizontal and the vertical, and then you mod it out by the image of the guys going in diagonally. And then you have the donor, and donor and receptor, those names will become clear in a second. The donor of A is, this time we have the kernel, the guys that are killed not by both, but by their by a composition of a vertical and a horizontal map. So the kernel of the diagonal map going out, modded out by the image of the sum of the two guys going in. So, the sums of the images. So the image of DH coming in plus the image of DV coming in. Now, with these four definitions, we can form some very naturally defined maps. Now, you may be wondering what these maps are. Well, these four definitions give us a nice little commutative square. And I like to think, I don't know if this is just a coincidence or if this is deliberate, but I like to think of these squares, which have been chosen to notate the receptor and the donor, as representing where they are in the commutative square. Because this is in the top left, so we've got the receptor of A, and it maps to both AH and AV. And then they go into the donor of A, like so. These are called the intramural or intra-something maps. And, well, how are they defined? Well, they're literally the identity on the representatives. So what it does is it takes a representative, because remember, these are all quotient groups. So it takes a representative, A, of one of the elements of your quotient group, and all it does is it sends it to whichever coset it represents in this quotient group. So let's take a look at why this works. If we're in the receptor of A, this means we're looking at elements that are killed by both DV and DH. And therefore, if we map it to AH, we are indeed going to get an element which is killed by DH. And therefore, we are going to get a representative in AH. So this element is going to be a representative of some element of some coset in AH. And the same thing for the vertical homology as well. Because it's killed by the vertical map, it will give us a representative of one of the cosets in the vertical homology. The last thing to consider is Will the representative of 0 map to representative of 0 in both of these homology groups? The answer is yes, because if you're 0 in here, then you're in the image of the diagonal map going in. But if you're in the image of the diagonal map going in, that means you're of the form dv dh of some a, we'll call it b. But because of this, that means that you're also just in the image of dv, which means you get killed by this quotient group. And then we can use the commutativity to say it's also of the form dh dv of b. And then now you're in the image of dh, so you're also 0 in the horizontal homology. And so these two maps here, going out of the receptor, those are perfectly well-defined maps and they're perfectly fine to work with. Now, what about the maps going in to the donor? Well, if you're killed by DH, then you're certainly going to be killed by the diagonal map, because if we just write the diagonal map of dv dh, if this thing here is 0, then dv of 0 is just 0, because dv is a homomorphism. And so and the same reasoning for the vertical homology. Again, just use the commutativity and you'll be fine. So we are going to get a representative of some coset in the donor. And what's more is, if we're in the image of dh, so we're representing 0 in the homology group, then we're also representing 0 in the donor, because if we add these two together, well, dh plus 0 is of this form, and it's also just dh of something. And so, same thing for dv. So 0 maps to 0, and this whole square is nicely defined and works. So you just take the representative in this quotient group, and you map it to the same element, but it will just be representing a different coset because it's in a different quotient group. So that's how that map is defined. Good. These are the intra something. I think they're called intramural, intra something. Basically, they have the word intra in it. And the reason for that is because we're only looking at A, and we're only mapping elements of A. Now, we're going to look at if we have some map F, which takes us from A to B. Now, we're still within the double complex, but we have this map F, which takes us from A to B. This gives us I'll put it in brackets like that. This gives us a map from the donor of A, that's where the name comes from, to the receptor of B, because it's sort of like A is donating B an element and B is receiving it, in a sense. Now, how does this map work? Well, what it does is it takes an element of A, the donor of A, and it maps it to DH. We're going horizontally here. It maps it to DH of A. Now, why does this work? Well, we're going to go through the same reasoning as before. So, is this a representative in the receptor of B? Well, clearly, it gets killed by DH, because DH of A is just 0. Good. Does it get killed by DV? Well, because the receptor of A is formed of elements of the kernel of the diagonal map, this means that dv of dh of A, by definition, will be 0. And so our new element here in the receptor of B gets killed by both dv and dh. So it does represent an element in B. Good. Now, is it true that an element which is 0 will get also mapped to an element which is 0 in here? Well, if you're 0 in the donor, you're of the form dH plus dV. If you apply dH to that, dH of dH dies, and so you just get dH of dV of some element, which is precisely of the form d diagonal of some element. And so it will be in the image of the diagonal map going in, and so it will be 0 in the receptor. And so 0 maps to 0, A gives us a nice representative within B. We're all nicely well defined. So these are called the extramural maps, because now we're going from A not to another group in A itself, but to B, the different module, I guess, we're working in. Now, with these definitions out the way, we're ready to state the famed Salamander lemma. So, okay, Salamander lemma. Here we go. Now I'm only going to focus on, there's two different versions of the Salamander lemma, but they're both proved in exactly the same way, so I'm just going to do one of them. So, if we consider a double complex and consider the following 4 elements. So we've got C, which goes down into A. We go from A across to B, and then down into D, like so. Given these 4 elements in a double complex, we have the following 6-term long exact sequence. Okay, we're going from the donor of C into the horizontal homology of A, and we go via the receptor of A. Then we go from the horizontal homology of A via our intramural map to the donor. Then via our extramural map, we go to the receptor of B. Then via our intramural maps, we go to the horizontal homology of B. Then via the donor of B, we make our way up to the receptor at D. And this, oopsie daisy, I claim is an exact sequence. And that is the statement of the Salamander lemma. Okay, so the good news here is we've basically explicitly defined every single map. And so what we're going to do is explicitly check every step. We don't need to do anything fancy. We're just going to check every single step of the way. And hopefully it's all exact. So, I'm just going to write. Okay, so let's just get things cracking now, shall we? So, the first step that we have to check is that the kernel of this map here is the image of this map here. So we begin by just considering A in the kernel of our map going from the horizontal homology to the donor of A. Then, what does this imply? Well, if it's in the kernel, that means it's 0 in here. And that means it's of this form, dH of A is equal to dH of B plus dV of C. What we're going to do here is we're going to apply the horizontal differential. And the reason we're going to do this is because A was an element of the horizontal homology, it's going to vanish, and so is dH of B. And so it's going to tell us some important information about dV of C. So this implies that dH of A, which is equal to 0, is equal to dH of dV of C. Now what does this mean? This means that our C is getting killed by the diagonal map, because the diagonal map is just the composition of dh and dv. Good. If C is getting killed by the diagonal map, that means that C is C is a representative within the within the donor of C. And so what this implies is that C, or maybe the equivalence class of C, is in the donor of C. Good. Now, why is that important? Well, that means that A was of the form dH of B plus dV of C. Now, dV of C is precisely what our map from C to AH would look like, because remember, our extramural maps, because C is above A, it's going to be sending C to dV of C. So this thing here is in the image of C, the donor of C to A homology. And what's more is that because we're adding dH of B, if you look at the definition of the horizontal homology, because we're quotienting out by dH, that means that this is also since this is also equal to just the equivalence class of dV of C. And so by this reasoning, this means that the equivalence class of A is equal to the equivalence class of dV of C. And so that means that A is in the image of our map going from C to the horizontal homology of A, like so. And so we've shown that the kernel is contained within the image. And so what we need to do now is show the reverse, which is that the image is contained in the kernel. But that's not too bad, because why not? Let's say A is in the if let's let A be in the image of our map from C to AH. Well, this implies that, oh yeah, because A is equal to dV of C, this is of the form dH of 0 plus dV of C, and so it's also in the kernel of our map from AH to AC. Like so. Good. Okay, that's the first step done. Now, second step. We need to show that the kernel of this map here, the extramural map, is the image of this map here. So, again, let's let A be in the kernel of our map from the donor of A to the receptor of B. Like so. Then, what do we have? Well, if it's in the kernel, that means, by the definition of the receptor, it gets killed by the diagonal map. And by the definition of our map, because we're going horizontally, this means that dH of A, which is the map applied to A, is equal to the diagonal map of something. So d h dv some b. Okay, good. Now what we're going to do is we're going to take away this dh on both sides. We're going to get that dh applied to A minus dv of B. The reason why we can split it up like that is because it's a homomorphism. So this is just dh of A minus dh of dv of B is equal to 0. And, well, what does this imply? Well, because we're going from the receptor into the we're going from the donor into the receptor. Within the donor, this boy here, A minus dv of B, this represents the same coset as just A. The reason for that is because in our original set here, we're modding out by the image of dh plus dv. Well, this is just this. These two differ by dv plus dh because this is just A plus dh of 0 minus dv of B. So they're within the same coset. And that means, well, because dh of A minus dv of B is 0, and this is true, this means that, well, A is in the image of our map going from the homology into the donor, because all this map would do is it would take our guy here in the horizontal homology and it would map you to this representative here, because it would map you to itself, which is in the same coset as A. And so A is in the image of our map here. Okay, good. Now, what we need to show that if it's in the image, it's in the kernel. So if we're in the image of this map, then so if we're in the image of this map, then what does this mean? This means that we're in the kernel of the diagonal map. And so, okay, let me write this out. A in the image of the map from AH to A, the donor of A, implies that A is equal to, if we're in the image, then we're getting killed by DH. And so, my bad, I got confused for a second. Because we're going from the homology, this means that A gets killed by DH, and so we have DH of A equals DH dv 0, and so we're in the kernel. Like so. Okay, good. I lost my trail of thought for a second there. Okay, good. So that's 2 out of 4 shown. And you'll notice that the hard part is going from being in the kernel to being in the image. That inclusion is normally harder to show. Okay. I don't really want to flip over, so I'm just going to rub out our guys. Just going to continue the proof. Okay, now, third point. What's the third point? Well, we've done this bit here, so we need to do this bit here. So, again, we need to show that the kernel of this is equal to the kernel of this. Equal to the image of this. So, let's let B be in the kernel of our map from the receptor of B into the horizontal homology of B. Now, what does this imply? This implies that, well, because the horizontal homology, if it's in the kernel, it means that B is equal to dH of some A, let's say. Okay, good. Now, what this means is, if we, yeah, so B is of this form here. Now, because it gets killed by both dv and dh, what we're going to do is we're going to take dv on both sides. And this implies that dv of B is equal to dv of dh of A is equal to 0, because dv of B is 0. And so this implies that A is in the donor of A. Yeah, good. Yeah, this is that one. Yeah, the donor of A. Good. And this implies that B is in the image of the map from the donor of A into the receptor of B. So let's review that for a second. So we let B be in the kernel, which meant that it was of the form of dH of A. And then what we just did is we take the vertical map on both sides, and we use the fact that we came from the receptor. Because we came from the receptor, that means that our B gets killed by both dV and dH. So if we apply dV, then dV of B gets killed, and so that means that dV of dH of A also has to get killed. So that means that A gets killed by the diagonal map, which means that it's in the receptor of A. Sorry, the donor of A, because it gets killed by the diagonal map. And so B must be in the image of our map from the donor to the receptor, because it's precisely of the form dH of A, where A is in the donor of A, because that's precisely how we define the map. And now let's go the other way. So let B be in the image of our map from here to here. What does this imply? This implies that B is equal to dH of some A, and well, that's literally the that's in that, yeah, that's all we need to show that it's in the kernel. Yeah. Of our map from B to the homology. Yeah, because what this would do is it would, our map from the receptor of B to the homology would just take us to the equivalence class of dH of A, which in the homology is just 0. Good. Okay, that was probably the easiest one. Now the final step, step 4, is showing this exactness here. So, you guessed it by now probably. Let's let B be in the kernel of the map from the horizontal homology into the receptor of D. Good. Okay. Now, what does this imply? Since we're in the kernel, it implies that, and again, our map now is the vertical map down. So this implies that dV of B is equal to dV of dH of some, I don't know, A, like so, because we're in the kernel, and so we must be of the form D diagonal. Okay, now what we're going to do, take away on both sides, very similar to the second part. We're going to have dV of B minus dH of A is equal to 0. And so what does this imply? this implies that, well, okay, we have that dv of this thing is 0, and what we also have is the equivalence class of B is equal to the equivalence class of B minus dH of A, because we're going from the homology into D, and so from the horizontal homology, and so if you differ by dH, then we're in the same equivalence class. And so again, what the image would do is the image would this implies that B is the image of this guy under this map here, because our map from the receptor of B into the homology would just map this guy to its own representative, which would be B. And so B is in the image of our map from B to BH. And just to finish it off, if we let B be in the image of our map from the receptor into the homology, then this implies that by the definition of the receptor, dv B is equal to dv of dH of 0, and so it's of this form, which implies that B is in the kernel from homology D. Good, okay. And that's all of the steps of the proof done. It was quite a long proof, but once you sort of see what's happening, the steps become, I think, quite routine. You just do a little bit of manipulation, use the fact that the squares commute, and that the differentials square to 0, and just all the definitions sort of come together nicely, and they're just enough. These definitions work out well, and yeah, we get this 6-term long exact sequence. And so I think what I'm going to do is in the next video, or in a video, future video, I'm going to take the Salamander lemma as true and use it to prove more well-known homological algebra theorems. I'm making a case for the Salamander lemma as an important theorem in homological algebra. Yeah, it's quite a satisfying proof, I think. It's sort of uses the understanding of quotient groups and stuff. And yeah, hopefully I'll be seeing you next week, or maybe even sooner than that. So yeah.